Well, if anybody's online right now, we're just gonna wait for one.
Sounds good.
For now. I'll plug that in. That's for an hour. Um, it is extracting. We'll talk about what it does. All right. Here, oh, we were. Yeah. How about now? All right. Cool. So, yep, everything should be good. Let's start then. Okay. So today's talk. This is going to be the third podcast for ACM Entrepreneurship. Today's topic is going to be currency, parallelism, and async IO. We will mostly be exploring this topic through Python because Python has a very rich library to interface with the operating system as well as also. Um, So first introductions, I'm Kevin. I am the technical director of ACM E, and today I have as guest Lucas. What is your
I'm a computer science major.
any sort of like leadership positions?
Yeah, so I'm currently the web chair for the iGEM development.
Nice, nice. What is your familiarity with Python?
I have a little bit of experience using it with data sets, using the pandas library. And then I've used like the basic, for loops, basic.
All right, cool. So today we are going to be talking about parallelism, what concurrency, why it's useful. So parallelism is something we find mostly useful in scientific computing. And the reason why that is because there's a ton of data that needs to be processed, and we're trying to minimize the amount of time that's spent processing on the data. Concurrency is very useful for web development. Any sort of input I/O operation where data needs to be moved, more so than data needs.
Exactly do those two things.
Well, parallelism will speed up all of your processes. Scale linearly depending on the amount of resources that you have.
Okay.
It maximizes your effective utilization of your resources. Concurrency is very much so the same idea, but concurrency maximizes your resources along the time domain more so on the computational domain.
Those are both just ways of like splitting up processing power.
Parallelism is about splitting up processing power.
Okay.
Concurrency is about maximizing time utilization.
Okay.
Which there are very similar concepts, but parallelism has to do more so with running the same computation on the exact same data on the same data sets. Well, the same functions on different parts of the same data set. Concurrency is a kind of catch-all where you're doing multiple things at the same time.
One CPU core or
Concurrency, you can have multiple CPU cores. Concurrent. Yeah. With parallelism, you are bound by a single process.
okay. It is a software thing.
Yes. Well, so if you have in parallel applications, if you have multiple, if you only have a single core, you're not going to gain any benefits from parallelizing your application. It's just going to be switching between time on the single CPU core. Versus for concurrency, what you end up doing is time sharing on the CPU.
Okay.
Okay, so let's get a little bit more into depth with parallelism. So unless you have a background where you need to be creating computationally intense research, parallelism isn't something that you see very common. That being said, the reason why we're starting with parallelism is I think it is a little bit more accessible than concurrency because concurrency you have to do a lot with I/O and event handling and stuff. Versus parallelism, it is mostly data processing. And I think when you're starting out with writing code, most of your code does have doing basic computations. Okay, so what is let's start off with talking about for parallelism. One of the things that we do in a research lab is extracting useful information. What we have to do is compare frames of a video to see what is the difference between each video frame. The idea is we want to select interesting frames from the video. So you can imagine a situation where I have a camera that's pointed at something and nothing really happens. And I only want to see what happens when something is moving in the frame.
Yeah, so you're comparing like one frame to the frame plus or minus 1, 2.
Yeah. If it's very similar to the frame, we don't really care about it. If something is moving in the frame, then we care about something. And then we want to see what. So in order to do this, we need to do something called a phase correlation algorithm. And the code for it is now.
Okay, that for.
So this mp.fft means a fast Fourier transform, and this is rather computationally expensive. It does take some time to run, and the question is, how do we make this faster?
Right. And so the fast Fourier transform is just kind of get the free. How does that help you, I guess, determine? Just like checking the frequencies and comparing the different.
Essentially, yes. There's a bit more than doing the uh, just doing the free fast Fourier. Ultimately, the idea is that this function, it gives you a scalar number based on how different they are. The important how this mathematically works is not really important. All that we need to know that is that performing matrix operations on frames is complicated. Okay. So whenever we're talking about doing parallel works, there's two technical questions that we need to ask ourselves. First one is, how do we split up our workload? Because if we have a certain data set, we want to have each CPU task working on a specific part of the data set, and we don't necessarily want any overlap in order to do repeat tasks. The second problem, which is much more difficult, is synchronization. So at the end of doing your tasks, you need to synchronize your workload.
Right. Make sure everyone's on the same page.
And so we're going to talk about these tasks individually, and we'll see how all that works. All right, so we're going to do parallelism.py. All right, so I'm going to type on one computer. You're going to type on the screen that everybody else can see. And so then, if you have any questions about what these functions do, you can ask me, and hopefully that will keep everybody on the same page, keep everybody engaged. So I'm not talking about really in-depth details.
Yep.
Okay. So first thing we're going to do is import the OS package from Python. And we are just going to first start off with spawning, forking is the technical term, a subprocess. But first, let's create some variables. So this counter variable, the reason why we are initializing it to demonstrate the fact of how fork clones memory space. That's something to keep in mind.
So fork is going to be what's parallelizing our process.
Fork basically allows you to spawn a sub. So if you just run this right now, get Python 3 parallelism.py. So fun fact, the fork function is only available on Linux.
Okay.
Yeah. Okay, so you actually want to print it.
This would not, you couldn't do this on Windows.
Not necessarily. And so if you guys notice,
this printing the child process is like so what this is counter, I'm assuming.
Nope, that's the process. If you get comments out the print counter line. It's Python. It's the hashtag pound. So
okay,
fork returns twice. When it returns the parent process, it returns the process ID of the child. When it returns in the child process, it returns 0.
Okay.
So when you call fork, it quite literally creates a fork in the road. And it will it will basically clone the memory space, and so the variable counter will be cloned. But the child process, if it increments the value of counter, it won't affect the variable in the parent process.
We're basically just duplicating whatever our state is.
Yes.
Very, very.
Oh, well. I'm going to do import times. For 1 second, please.
Sure.
So it only prints out 0.
Right. Then it's now it's printing out 10.
Oh. Okay, so basically what happened is this. The child process finished the for loop and then exited, and now it's running the same code as the parent process. Because the parent process is still converting out the counter. It's 0 on the parent side. But on the child side, it's still 0. So basically the point of this is to demonstrate the fact that when you fork a process, most variables will not be affected. You can't change the variable in the child process and have it reflected in the parent process.
Right. So when we fork, we're then running the code twice here for the parent and the child.
Yes.
And so the child is doing this for loop here because it's
you can highlight the things that you're talking about.
Good idea. Rather so the child is running this here because child is 0. By counter goes up to 10. And they both run this?
Yes. Because this the clause protected by the if statement does not run for the parent process.
Yeah.
But this part runs for both.
Right. That makes sense.
Okay.
And so then I guess looking at the output then, we're getting some unevenness with we're getting 2 10s and then 2 zeros.
Mm-hmm.
That just like I don't know what's causing that to happen, because it should just be 110, 10, 110.
Because now
it was earlier, right?
Because now the child process has returned. Well, it hasn't returned yet. It's now executing this while loop 2.
Okay.
So in the child process, the counter has reached 10.
Yeah.
But
it's doing this.
And so now the child process is printing out the value of counter.
Right. But then down here, why is it child printing out twice? And
synchronization.
Okay, it's
not supposed to.
It's just some weirdness with trying to do them both.
And so now it should do exactly what we want it to do. Which is only print out zeros.
Right. Because now it's only printing out.
because now only the parent process is executing the. Here you see it is the
Yeah. And they're each doing their own thing. That makes sense.
okay. So including all processes. So if we want to say divide up the workload, instead of having a one counter variable, we're going to change it to a list. How many CPU cores do we have? Let's make it 16. We're going to create four child processes.
Enumerate method do?
Hmm?
Enumerate method? Or enumerate?
Enumerate basically gives you the index and the elements.
Okay, all right.
Not four.
Up four?
Not four, yeah, because four is the number of CPU.
Okay. I what is this output I get?
So basically, what happens is these represents the tasks that are done by each core. So core
Okay.
1, core 2, well, core 0, core 2, core 3, core 4.
Okay.
And as you can see, core 1 handles the first elements and the fourth element, 8th, 12th element.
I see.
And then it handles this one. So you can see it's staggered.
Right. Yeah. Yeah.
Right. So now this is a very easy way of dividing up our cores.
Okay.
So then the question is, okay, we need to synchronize this because we don't want to have 4 different arrays with different values. We want to have one array with all ones.
Right.
So now the question is, how do we do that?
Right. We would need to then need a way of condensing back into one state from four different programs running.
Mm-hmm.
Want me to spitball an idea, or
Sure.
are you gonna? I was thinking, you could put it in a file, have them all write to.
That is exactly what we're going to do. Except we're going to use a shell. We're going to redirect it to a separate program which synchronizes it again.
Okay. Is that async.py?
No.
Okay.
But first, so now we need to print it out in a format that our next program can understand in a way that we can actually merge all of the data together.
Okay. You're gonna modify our print function.
Mm-hmm. Okay, run the program again.
Outside of this for.
Oh, you need to put it.
No zeros.
Oh, yeah, we need to put it into the next folder because we only want to print out the process if.
Oh, so type it down one more.
Yeah.
Okay. So now here are the numbers of all the ones from that previous output.
Oh. Yep.
So now we can see them more clearly.
So as you can see, if the viewers can also see it, this is not in order. The index followed by the value. So here the 1 represents the result of a finished computation. And see, none of this is in order. But that's okay. We don't need it. We don't need the results of a parallelized computation to be in order. If we did, we wouldn't be using parallelization. We would be using concurrency.
Okay.
Because then we can use different synchronization primitives in order to get everything together.
Just the fact that we have the results matter. The ordering is something we can deal with.
Yep. And so now we're going to create a new file called sync.py. And the idea is now we are going to take the results of this program and then synchronize it. For sys.
All right. We're just taking the data from but and then just sticking it in.
Mhm.
Right.
Well, now nothing's going to happen because we didn't actually.
Right. So we need.
So now we need to actually run the other one and then pipe the inputs.
Okay. All right.
So this is the pipe operator. So we're
Yeah.
going to take the inputs of the other one and into. Basically, pipe broke. So basically, what's happening now is that this process never exits.
Right.
Let's make it exit in
Oh,
5
so the
seconds.
piping never goes
Yeah.
through.
So the exec accept part never actually runs.
That makes sense.
So now that we have actually synchronized all of our data, if we want to sort it, we can.
Because we now have an data.
Yeah.
So we can.
And so now it's all sorted.
All right.
1, 2, 3.
Cool.
All right. So
That would theoretically be faster than just doing it all one at a time.
yes, but again, this is a very contrived example because obviously no processing is actually being done here.
Right.
All we're doing is we're setting this flag to 1 as a way to indicate yes, we've done the processing.
The setting the counter to 1 is just a stand.
Yes.
Something theoretically very
well, not necessarily complicated, just time
intensive. Yeah.
And so the practical application is in framediff.py, right? Run through the code here. The phase correlation algorithm, this takes a lot of time to run.
Right.
And so this is the function. This part of the code reads all the data from the video, puts it into the frames. And much like how in parallel.py, we had this array here that contains all of our data that needs to be computed.
Okay.
And so now here have core and range and cores. This is forking the child process in order to distribute the work.
Right. And so this is just however many cores are available on the whatever machine this is run on, fork it that many times.
And here we have the same distribution type where we use a modulo in order to calculate the frames. And here we get the result of the phase correlation. Now the phase correlation does take some time to run, and we don't necessarily need it to be in order. So now we write it here. This prints it out to standard output, which acts as our synchronization. And this is the debug. This is just, in order to look at it.
Yeah. So when we have this for loop, and call child.os.fork, does it then on one core just continue running the rest of the for loop, and on another core just go straight back up to the top and do this again?
So on the parent core is the one that is spawning the child workers.
Okay.
And only in the child worker does it keep on going.
Okay.
Now,
because child equals 0, so if it's parent, just go back up to the top.
Yes, but if it's a child,
right,
it executes this part.
Okay, yeah. I get that now.
Mm-hmm.
And with semaphore, I'm assuming that's just some tool used.
Semaphore is a way of doing a counter. So if we go back to here, and we import multiprocessing for. I'm going to set the initial counter value to 8. So the with sem basically allows us to acquire the semaphore. And then once the block exits, it's going to release the semaphore. Okay. So we still need this loop.
Okay. I don't need. Waiting for that time. Well, okay. All right, and so semaphore is just counting up, and it's like a synced count. Okay, cool.
So semaphore, because it is a multiprocessing primitive, the value of it will be shared by processing.
Right.
But every single time you use a synchronization primitive, you run into overhead.
Okay, and what is overhead?
Basically, because every single process needs to agree on the value of semaphore, every single time you do a little context switch like that, it slows down your program just a little bit.
I see, okay. You just need to do a bunch of just checks between. That makes sense. And I guess max, you're saying the max for semaphore that what this is? That's why it's not going. No, we're just never going. And then we're just printing out. And so it's printing out semaphore every single fork then? Just, or no, we're exiting in all of the child forks.
Yes.
So this is only happening in. Okay. Then it's actually being modified by
this exit. I think it's not releasing the semaphore.
Have it over one?
Yeah.
How it's supposed to be doing?
I'm expecting the counter to go down.
Okay. Doing it decrement itself? What would cause it to go down?
The fact that the semaphore gets released.
Okay.
Well, mystery for another time. Okay, so now that's parallelism. Now let's talk about asynchronous I/O. Okay, so I am actually going to type it here, just because we are running short on time.
Yeah.
Okay, so async I/O is for, instead of doing multiprocessing where we need to run data, we want to have inputs. So the nice thing about async I/O is because we're running the same process space, everything is shared.
We don't have the different states.
Yes.
Like we did.
We don't clone off our memory space, and everything is going to be within the same exact state.
Okay.
So one of the things with async is if we want to say have a loop that handles input from our keyboard, we can do something like this. We need to use the async def function.
All right.
Actually, first let's talk about the event loop. The event loop is the thing that manages all of our threads. Now, async I/O is a single-threaded application. That being said, async means that it is a program level code for multi-threading. It uses a very similar concept to threads, but it's at the user level instead of at the kernel level, and multi-threading is done at the kernel level.
Okay.
So loop essentially is almost like a mini operating system that manages all the states of our program.
Okay. And so it's just kind of like one controlling running program that's controlling all the other asynchronous stuff.
Yeah. So if we just do loop that run forever, it's never going to stop.
Stay monitoring the asynchronous stuff.
Yep. So what happens if we actually want to do something with async? Loop.run in executor is one of the few thread safe. Well, it's not really thread safe. It's effectively what it does is it runs this program in its own thread.
Okay.
And this allows us to interop between multi-threaded applications that relies on blocking threads within an asynchronous context. So within this async def, we're in the async context, but the input will block your thread. It will block the main thread if you are using inputs. Now, if you don't know what input does, in Python, input is a way of reading stuff from standard input.
So input will block the thread when? I guess the idea of, you said this run executor creates its own thread, right? And so that's one of the, I guess, yeah, threads that's going to be managed then by.
Well, let's just look what happens if we get synchronized input.
Okay.
So this will never. So input will block. Nothing. You can't do anything else.
It's going to stop there.
Yeah.
But then the run in executor means that.
Run an executor
means it won't block.
Means it won't block.
Okay. It'll just essentially wait for an input and then route the program back.
Mm-hmm.
Okay. That makes sense.
And the nice thing about async IO is that you can easily share data between coroutines. So now we're going to add it into this loop, into this data loop, and then we're going to async the
different function.
Mm-hmm. Async IO.sleep is how you yield control back to your event loop.
Okay. Basically, we're waiting for async IO.sleep to happen.
Once
after control has been given back to the event loop, then we run print data.
So every single time we wait for async IO.sleep, we are transferring control back to the event loop.
Okay.
Right. So once we yield control back to the event loop then delegates the next task, which is up here, which is get input. So every single time we call await, we're saying, okay, we are going to give control back to the event loop, and then we're going to let the event loop decide what to do next. It can either return back from this await statement, or it can just do something else.
Right. And so then the rest of that specific function is waiting for the return back. The loop can decide whenever it wants.
Yes. Group that, create task. So every single time, whenever you have a program that's running, you need to have a call stack.
Right.
When you call loop.createTask, createTask basically tells the async IO library to create its own execution stack for each of these coroutines.
Okay. So we now have different executions, different stacks.
We have 2 execution stacks that are running independently.
Okay. And so then one of them is printing out everything that's been printed, and the other one is just printing out. They're basically each just going to the stack and putting itself back on the stack.
Not necessarily. So basically what happens is right now, we're just printing out hello.
Right.
Every single time we print out the data, we're just waiting, we're calling sleep, we're sleeping this thread.
And we're while truing back into that same function.
Yes. And now we're transferring control back into the get input loop.
Right.
And loop.run and executor is now waiting for input. So it's still waiting for our inputs.
So there's only been one call to each of these get input and data functions. There's just a while true loop, and the program's just deciding we're going to hop back into these.
Exactly.
It needs to.
It's just hopping back and forth based on some event. The event in this case is whether or not we press enter. So the moment I press enter, this part returns true. This part returns the world part. It prints the result, and then it appends the data.
Right.
We are still within the control. It doesn't yield control back into the event loop until we call run and execute it again. And so now it's still waiting for input. So now it comes back.
Right. And unlike parallelism, we're only ever doing one thing at a time. We're just deciding smartly which thing we want to be doing.
Yes. And so if we just had this, right, if we get rid of the await.sleep, it doesn't matter what we do.
Right, because that while true loop is just taking up everything.
Yeah. If we just do pass here, right, it's not going to print out anything. It doesn't matter if we keep typing, because it's always in this while true loop. It never yields control back to our code routine, back to our main event loop, and therefore loop that run executor can never ever return.
That makes sense.
And so now, whenever you're dealing with user level threads like this, you need to have, you need to be very conscious about how you're managing your time, and when is yielding control back to the event loop.
Mm-hmm. Now we actually have
Exactly.
hopping.
So this is, again, another contrived example, but now that we have like a baseline with a contrived example, let's see actually in practice. The application of it will be here. Let's look at our simulation. There's 1,000 lines of code, but I will show you all where the important part. So a simulation basically runs every single iteration. It does all the computations. Okay. Yeah. So as you can see, our run function for the simulation is asynchronous. Part doesn't matter. Not important. Not important. Not important. But essentially, this loop handles all the simulation that's being run. For I in range 1, until the end of the simulation, we're going to run the simulation. Iterate once. Right. And as you can see, at the very bottom of this loop, we're going to sleep and therefore yield control back to our main event loop.
Back to the loop. What other things are we going to be trying to run that loop? Like, is there some input you're trying to take it in?
That is down here with the shell function. This essentially allows us to control the simulation through standard I/O.
Okay. You want to have like a bit more of a hand in the simulation while you're running.
Yes.
That makes sense.
So for example, if I want to run the simulation, what was it? So now the simulation is running,
right?
But I can pause it.
Okay.
Now I'm pausing the simulation, and now I can check the state of the simulation, see what's going on. This is a worm simulation. This is a population dynamic, and each of the worms are represented by its own agent. And so every single iteration in the simulation, we're calculating the next state of every single agent.
Right.
Now you might think, well, you can parallelize this. Oh, that's true. You can actually spawn off multiple cores and have it all interact with each other. But again, the fundamental design question whenever you're working with parallelism and concurrency is specifically with parallelism, is it worth all the extra overhead of spawning off multiple workers in order to do the computations? Right. Most of the time, it's not.
How much connection or how much communication do these children need to have between?
A lot.
Yeah.
Within the context of the simulation, yes, it's a lot, because every single iteration depends on the next one. So you can parallelize horizontally across every single agent, right? That you can parallelize in the computation. But after the iteration is done, you need to synchronize everything back into the main program. And the main program needs to spawn another set of processes again.
Right. Makes sense. But in this case, is the synchronization being used for anything other than just kind of controlling the program?
Well, yes, the state of the simulation itself.
Okay.
For example, in this situation, the more worms you have that are being reproduced and spawning, the less food that there is, and the less food that you have, the less it affects how many worms can survive.
Right.
So you can imagine if the simulation says I want to create a lot more worms, it's going to reduce the amount of food that's available to the simulation on the next step.
Okay, and that's being controlled by that's just part of the.
That's part of the iterative nature of a simulation.
Okay, that's just part of the simulation itself. That doesn't have to do with the synchronization. Okay.
Now, eventually, if you get to the point where you have a ton of things to simulate, think physics simulation and body simulations where you're possibly simulating billions or trillions of particles.
Right.
Then it makes sense to start parallelizing.
Okay.
Because then the cost of synchronization is so low compared to the computation cost of simulating trillions of particles.
Right. Even though there's a big communication cost.
Yes. Even if
it doesn't matter because just the cost of doing it as a whole.
Yeah.
Parallelization, you're never.
So if you just run the simulation right now, the first 10, 15, 50 time steps, it goes kind of fast because there's just not a lot of worms alive.
Right. Now you're starting to have more worms, and so. And so eventually, would we get to a point where it'd be faster to parallelize? Yes. Okay. Very much slowing down.
Okay, so now we can increase our food count. We're gonna feed them every 3 hours. And now we're gonna see that the amount of worms that we have grow exponentially.
$1,000 extra worms.
Now we have 100,000 worms.
Yep.
Again, remember, we're basically simulating. The point of this project is to simulate, based on the environmental conditions, how many worms are going to alive, how many are going to die, how many is going to transition into different life stages like larva and etc. The exact details is not important. The idea is now we're talking about scale.
Right.
This is 100,000 worms. Now, how many is the next time step?
I'll guess 300.
This is going to grow exponentially.
You can only jump what? Because some of them have huge ones.
So I typed in pause, but as you can notice, and nothing's happening. Well, the reason why nothing is happening, look how many we have. Over 1 million worms alive.
Oh wow, that was a big jump.
Yep. So here, if we are trying to say compute the effects of millions of entities, whether it's bodies in a physics simulation, whether it's worms that need to eat food, reproduce, lay eggs. This is when you would say, okay, we want to parallelize this. Right. When the number of calculations is so huge that it makes sense to synchronize between every single time step.
Yeah. So wild, just to for one. The times it has even fully ticked over. The times it hasn't even fully ticked over yet. We're still paused.
We're still paused.
Right. So yeah.
We can still start the simulation.
Yeah.
But it's gonna take forever.
Right.
There's a good chance it's not even gonna start. We're not gonna make it to the next one. So this is at 70 time steps we had 100,000. At 80 time steps we have.
Oh, did you get to 80?
One? Yeah.
Okay.
We got 1.5 million.
Keeps growing at that rate.
1.5 million is this is all being done on a single CPU core, so it's going to take forever.
Yeah. In that case, privilege. I don't know how many cores you have. Read down by.
So we have 3 minutes until the end of the podcast. If you guys are listening or watching in, I hope this is kind of helpful. This is really just a kind of a high level overview of the different techniques that we can use when it comes to doing task distribution, handling it I/O. There's a lot more. It goes a lot more in depth. We can do something called WebSockets. If you guys are still interested in learning more about async I/O stuff, the next practical application will be using the WebSockets library. It's basically allows real-time communication between two processes, between, like, say, a web browser and a server, where you don't have to do any sort of polling in order to get the state of the server. And it also allows you to do some really cool stuff like data streams and doing live graph renderings. So let me know if you guys are interested in that kind of stuff. But we are out of time. 4 minutes, but I think we're good.
Thank you for having me.
Yeah.